We often treat education as an intuitive act, a spontaneous exchange between a charismatic speaker and a willing audience. But moving complex information across the gap from one human mind into another requires a highly calculated assembly. Pedagogical systems operate under the exact same constraints as structural engineering. They bear loads, they span distances, and they fail catastrophically if the underlying math is wrong. This architectural blueprint of classical learning models illustrates how educators construct knowledge. A lesson plan acts as a schematic, determining exactly how raw data is stacked and supported in the learner's brain. There is no single flawless mechanism for teaching. Because humans process data at different speeds and under different conditions, instructional efficacy becomes a dynamic optimization problem. This Venn diagram shows the three variables that dictate success. An effective system emerges only where the nature of the subject matter, the aptitude of the student, and the specific constraints of the environment perfectly intersect. To optimize this intersection, we have to stop looking for simple answers and instead deconstruct the pedagogical machinery, from its macro architectures down to its smallest internal gears. The first step in deconstructing this machinery is distinguishing the overarching framework from the individual components driving it. We separate the broad teaching method from the specific tactical actions. This illustration maps that exact relationship. The method acts as the structural casing, the complete system boundary. The tactics are the specific, interchangeable gears mounted inside, like asking a targeted question or prompting a debate, which physically drive the student forward. These tactical gears cannot spin at random. They are constrained by specific logic vectors but determine how the data enters the student's perception. This chart diagrams those operational pathways. The top left quadrant shows the inductive vector. Here, the instructor feeds the student multiple specific examples, forcing the brain to eventually extract a broad, general rule. It operates with high efficiency in subjects like language syntax and grammar. Conversely, the deductive mechanism is the exact mechanical inverse. The educator hands the student the universal rule first, then requires them to test and prove that rule against a series of localized examples. Below that, we see the structural logic of fragmentation and assembly. Analytic logic shatters a complete concept into its component parts for close inspection, while synthetic logic forces the student to take disparate pieces and assemble a functional whole. Selecting the correct logic vector is the foundational engineering choice of any lesson. If you pick the wrong trajectory, the data simply deflects off the student's existing mental models. In the mid-19th century, philosopher Herbert Spencer laid down a strict axiom for educational design. Instructors must minimize direct telling and force maximum self-discovery. This creates a difficult engineering problem. You cannot immediately hand a novice a complex abstract theory. The cognitive load causes immediate failure. You have to physically scaffold their perception from reality up to theory. This three-dimensional funnel details that scaffolding. The base layer is the object method. It relies entirely on concrete, physical manipulation, like using physical marbles to teach early arithmetic. It locks learning strictly to sensory input. Once the base is secure, the structure ascends to the illustration method. The physical objects are removed and replaced by two-dimensional representations, analogies, and maps, gently increasing the abstract load. Finally, we reach the apex, the lecture method. This is a high-risk environment operating almost entirely on abstract auditory data, suited strictly for advanced cognitive states that have already mastered the lower tiers. Operating at this level of abstraction is dangerous, but the transfer of highly complex, interconnected systems eventually requires direct lecture. The question is how to execute it without collapsing the student's attention. To solve this, the philosopher Johann Harbart designed a highly specific, sequenced algorithm to make abstract lectures structurally sound and highly digestible. This staircase model lays out Harbart's algorithmic progression: preparation to prime the mind, presentation of the new data, comparison to existing knowledge, generalization to extract the broad rule, and application to test it. This sequential scaffolding is not a crutch, it is an architectural necessity. Skipping steps causes the entire mental model to buckle under its own weight. For centuries, the top-down lecture hierarchy dominated, But as society industrialized, it rapidly required adaptable problem solvers, not passive listeners. The old architecture failed to scale to this new demand. Progressive educators realized that patching the old system wouldn't work. They initiated a complete structural inversion of the classroom itself. This structural diagram contrasts those competing models. They dismantled the rigid, teacher-dominated pyramid on the left and engineered a radial, decentralized network on the right, placing the student at the center of the data flow. The catalyst for this shift was John Dewey's philosophy of active heuristic engagement. He argued that comprehension was a byproduct of action. Under this model of autonomous discovery, the teacher's role is completely stripped of its broadcast function. The instructor becomes a passive environmental guide, manipulating the constraints of the room rather than the flow of answers. This graphic outlines the mechanics of that shift. Frameworks like the heuristic and project methods were engineered specifically to trigger organic problem solving, forcing the student to build the tool required to pass the obstacle. Educator Helen Parkhurst whose progressive philosophy and weaponized it as a literal architectural redesign of the school building itself. This floor plan documents Parkhurst's Dalton Plan. She abolished the generalized, one-size-fits-all classroom entirely. She ripped down the walls and rerouted students into highly specialized, subject-focused laboratories. Within this layout, students manage a completely autonomous workflow. They navigate between labs at their own pace, fulfilling highly specific assignment contracts and tracking their own metrics on graph cards. To truly change how a student's brain processes information, these pioneers had to physically and systematically dismantle the very rooms in which they were taught. Modern educators inherit the results of this historical teardown. They possess a massive, highly complex repertoire of competing architectural frameworks. This architectural drawing displays Mahatma Gandhi's Wardha scheme, a framework designed entirely around physical handicraft to foster societal self-reliance over abstract academia. This table catalogs just a fraction of the child-centered frameworks available today, each engineered to exploit specific sensory inputs and environmental conditions. And alongside those progressive models sits an equally dense array of technical, logical, and instructional variations, ranging from Socratic dialogue to linear programming. Because of this sheer volume of highly specialized tools, dogmatic allegiance to a single teaching method is essentially architectural malpractice. This final diagram synthesizes the reality of educational design. The optimal method is never static. It exists strictly at the intersection of the student's immediate capacity, the rigid demands of the subject matter, and the specific capabilities of the teacher. True pedagogical mastery, the absolute mark of an educational architect, is the ability to read the terrain, select the appropriate logic vectors, and construct the exact mechanism required to permanently build knowledge in the mind of the student.